All right. Hello, everyone. It's my pleasure today to introduce my work on anomaly detection in connected and automated vehicles using augmented state formulation. Okay, this work is done by me, Dr. Nanda Masood and Dr. Anahita Hojandi. So let me first briefly introduce the background. Our current transportation system is under the transition from the traditional transportation system to a highly connected, automated, and intelligent system as a result of the rapid emergence of connected and automated vehicles. And there are lots of sensors are used by the CEV. And as the vehicles and infrastructures become more interconnected, the vulnerability of their sensors to faults or malicious attacks also increase. So we have two challenges for now for the CEV safety or the sensor safety of the CEV. The first challenge is the sensor anomaly. It can come from either sensor faults or a malicious cyber attacks. And the second challenge is the measurement noise. Okay, so most of the time the sensor measurement are kind of noisy. It can come from either communication channel noise or sensor background noise. Okay, so our research goal is how to smooth the sensor rating and detect those anomalous sensors in real time in order to avoid a fatal accidents. So in this work, we proposed a filtering techniques and a fault detector. So we construct a state space model using an augmented state formulation, and we estimate unknown variables based on noise measurement, and at the same time, we detect the anomalies based on innovation or residual, which we will introduce later. Okay, so we have several assumptions for this work. So the first assumption is the vehicles are under our car following model. Second assumption is there's a time delay tau applied to all the input of the car following model. This tau is not necessary to be a constant. It can be a stochastic. Also, we assume that anomalies come from either sensor faults or from an attacker that just inject random and falsified data into the sensor measurement and trying to cause the wrong estimation of the state variables. And finally, we assume the isolation for each vehicle is bounded and within the interval, A min and A max. So now let's go to the problem formulation. So we consider a traditional or well-known car following model formulation. So this representation of the equation one is basically is a most standard form of the car following model. And if we define a state vector of in a continuous time as the Sn, the Sn is, includes the location of the vehicle nth vehicle, xn, and also the velocity of the nth vehicle, let's see, vn. The nth vehicle is the following vehicle in this case, and the leading vehicle is n-1 vehicles, okay? And also we define the input vector, u, n, t, at time t, defined as the location and the velocity of n-1 vehicle, which is the leading vehicles. Okay, so in this situation, we're assuming that the following vehicle is capable of receiving the speed and location information from the leading vehicle, either from a DRCRC signal or from other communication channel or method. Okay, so after using the state formulation, using the new state, and we can recast the equation one as this function or this state transition model of the state, okay, the state variable Sn. So as you can see, that this state transition model is a function of multiple state or see multiple time, right? So this means that this state transition model cannot be directly applied to many Markovian-based filtering techniques. So in order to apply a Markovian-based filtering techniques, for example, Kalman filter, we are using an augmented state formulation. So basically, the key idea is we define a new state variable as tilde, such that it's basically the same as the SN, but instead we just add one more dummy variable here on the third row, and this represents um, uh, the integration from time t to time t plus tau of the acceleration of the four-wheel vehicles. Okay, and we have to assume that this sigma is changing really slowly because it actually represents the background bias of the cumulative arrow. Okay, so which means that by this assumption we'll introduce some arrow, and we have to use a process noise to represent all of the approximation error. Okay, but in this way you can see that in equation 3 we are kind of connect original state transition model to our new defined state variable S tilde. All right, so now we can rewrite the equation 3, the original state transition model, in the form of the S tilde, as you can see in equation 4. And the function G represents the motion model, and the theta T represents the process noise, which represent the error introduced by approximation and modeling accuracy. Okay, and now using the new augmented state formulation, we can get the continuous time state differential equation with discrete time measurement. Okay, and the continuous time state transition model represents the intrinsic nature of the vehicle moment, and discrete time measurement model represent the digital sensor sampling. Okay, and we also consider a more general setting when the time delay is stochastic. We consider a linear model of the tau s, denote tau s as the stochastic time delay. Then the tau s equal to tau plus a kappa. Kappa is a Gaussian distribution. It's according to a Gaussian distribution. And we also assume the leading vehicle's trajectory obey a linear model. Okay. And because we don't know the leading vehicle's motion model most of the time, so we assume the acceleration of the leading vehicle, which is n minus 1t, it's a Gaussian process with zero mean and variance sigma 2 square. Okay. So now we can get make such a claim when we get a random time delay tau s, that is equivalent to adding noise into the input vector un t minus tau with fixed time delay tau, and this can cause a non-zero mean process noise theta t. Okay, which means that, what does that mean? So this means that when we have a stochastic time delay tau s, the continuous time state transition model with the discrete time measurement can be recast from the current form to the new form. So basically you can see that it used to have a stochastic time delay tau s of the input vector. Now it's equivalent to a fixed time delay of the input vector, but we might have a non-zero mean process noise. Okay. All right, and that can cause a problem, and we will mention later. So using our augmented state formulation, we can somehow mitigate this error. Okay, and for filtering and detection, so we're using augmented extended coming filter for filtering. Okay, it can deal with a nonlinear motion model, and it can smooth the sensor reading at the same time. And for detection part, we are using Chisquare detector. The Chisquare detector constructs the Chisquare test statistics to classify the anomalies, and it actually constructs a circular boundary over the origin point. Okay, and these two parts can be combined or can be conjunct with each other. And yeah, I'm not going to go into the details of the AEKF today, but it just basically has the two part, prediction part and the update part. So the prediction part predict the state, and update part is kind of like combine the actual measurement with the prediction we already get, and to generate the estimate of the actual state. Okay. And the detection method, we're using Chisquare detector. So it basically construct a Chisquare test statistics and determine whether the new measurement falls into the gate region with the probability determined by the gate threshold psi. Okay. And so it's a gate is defined as you can see the Z here is actually a measurement. The Z hat is the prediction generated by the computer, and S is the covariance of the innovation. Okay, and the innovation is exactly defined as Z minus Z hat. Okay, so the chi-square detector in actual is defined as the innovation vector transpose times the inverse of the innovation covariance times the innovation vector. Okay, and this actually constructs a symmetric boundary over a 0 point with the radius square root of the psi. And this can cause a problem sometimes when, for example, so ideally the innovation should be a zero mean Gaussian variable, but it becomes non-zero when there's a bias in the background. Okay, it can come from either stochastic time delay or inaccurate model, and also the chi-square detector will not be a good. So the chi-square detector will not be a good detector in this situation, as you can see in this figure. There are huge amount of false positive in this case, where the blue curve will be the decision boundary of the chi-square detector, and the scatter plots are the innovation sequence. Okay, so we have to move this boundary towards actual centroid of this scatter in order to get a fair decision boundary. Okay, and the augmented formulation will compensate this potential bias. So for case study, we'll show now we're using the dataset, simply pilot dataset generated and collected by University of Michigan Transportation Research Institute. We're using a well-known intelligent driver model, IDM model, and we are using four types. We consider four types of anomaly, which are instant, noise, bias, and drift. These four types of anomaly are simulated in the testing dataset. Okay, so the duration and magnitude of each type of anomaly are generated randomly. So these two figures basically shows how the dataset we're using looks like. So this is the result of our experiments. So the table 1 shows the error under the curve score, which is AUC score. So AUC score basically represent how good the detector is. It's error under the curve of the ROC curve. Okay. So the higher AUC curve means the better performance of the detector. And we have the two models. Model 1 represents the traditional EKF with IDM model and chi-square detector. Model 2 using augmented EKF with IDM model and chi-square detector. So as you can see, when we have a time delay tau greater than 0, then the model 2 has a better performance under 3 settings. Each setting represents a different anomaly parameter or anomaly rate. So for setting 1 to setting 3, we become the anomaly become much harder and harder to detect. Okay. So as you can see, when tau equal to 0, it looks like we're not gaining performance by AEKF. That is because when tau equal to 0, there's no potential bias in the process noise. So using augmented state formulation will instead introducing some noise into the state transition model. So in that way, we're losing some performance when the tau equal to 0. But when tau becomes larger than 0, we're getting more and more performance gain. Okay, and in real life, tau is really hard to be 0, right? And for second table, it shows the mean innovation for each state variable and the mean square error for the two models when the anomaly rate is 0. And you can see that again, similar result, like when the tau is greater than 0, we get smaller MSE for the model 2. And we also can see when we get a non-zero time delay tau, the mean innovation value of the location for model 2 is much better than mean innovation value of the location, right? You can see the mean of the location, mean innovation value of the location in model 1 is much larger than the second one. Yeah, that's how this AEKF will compensate the potential bias in the innovation. So this, yeah, by the way, we are using stochastic time delay in the previous two tables. And also this figure shows the scatter plots of the innovation sequence for the two models. As you can see, for AEKF, the scatter plots are much more concentrated. In this way, we can avoid lots of false positives, right? So finally, conclusion, we proposed an observer-based method that combines signal filtering and statistical anomaly detection techniques together in order to improve the safety for CV. We utilize the AEKF to smooth sensor rating of the CV based on nonlinear car following model with the stochastic time delay, and not necessary, but with a time delay, where the leading vehicle's trajectory is used by the subject vehicles to detect sensor anomalies. With classic Chisquare fault detector in conjunction with the proposed AEKF for anomaly detection, and we consider general setting when there's a stochastic communication time delay in car following model. And finally, we provide numerical experiments demonstrating our result. And this concludes my presentation today, and thank you.